Hello and welcome back to Physics 201. In this video I want to do a couple impulse momentum problems. These are going to be a little bit different thematically than the collision problems, although they're still going to deal with the concept of momentum, right? Although we won't be focusing quite as much on the conservation law in these videos, but these couple problems should be very helpful for whatever in-class exercises and exam problems that you're going to have to do. Okay, so let's talk about impulse for just a moment. Let me mention what I mean when we're talking about impulse. So recall that in a previous video we had defined momentum just as P is m times v, right? Mass times velocity. All right. So what I'm going to do is I'm going to focus on a slightly different definition of this. What I'm going to do is I'm just going to take the first time derivative of both sides of this equation, so I get something that looks like this. There. And in this equation, if we assume the mass is constant, right, then I get dp dt is m dv dt, which is just mass times acceleration, right? And that's, of course, force, right? So this is, we could think of this as another way of writing Newton's second law, right? dp dt is equal to the force, right? So if you have some object and you're exerting a certain force on that object, you're going to change its momentum, right? And what I mean when I say impulse is simply impulse is the change in momentum, right? So that's it, right? So the impulse is the dp, right? Or p final minus p initial, right? So this is all I mean when I say impulse. It's a very simple definition, right? It's just change in momentum, right? Okay, but this is going to be a very important relationship, right? So this is another way to define momentum, right? In fact, when Newton first stated his second law of motion, right, he didn't state it as F equals ma. He stated it as F equals change in momentum over change in time, or dp dt, just like we've written it right here. Okay, so I think that's pretty straightforward. I don't think that's too hard to follow at the moment. I want to use that definition to go and approach a couple problems, right? So for the first one, what I want to imagine, or what I want to ask you to imagine, is something like a machine gun that's set up on some kind of mobile platform, right? So maybe the platform is on a track, right? So maybe it's a wheel track or an air track or something that lets it move freely, right? That's the point, all right? So maybe we've got a little stand here, and there's the thing there, right? And it shoots bullets out in this direction, right? So what I want to do is give some set of parameters and then figure out what we can learn about the motion of the cart as a whole, right? So here's the question, right? Let's say that I have a 1,000-kilogram platform, right? So the whole thing in total is a mass of 1,000 kilograms. Let's say that weapon, whatever it is, fires 10 rounds, right, or 10 bullets per second. Each bullet, let's say, has a mass of 100 grams per bullet, and each bullet is fired with speed 500 meters per second. There. And so those numbers aren't going to be exact for any particular weapon, but they're going to be close enough, and they're going to make our lives a little bit easier, right? They're nice, kind of factors of 5 and 10 that make things easy to work with. All right. So what I want to know is, given these specifications, what is the platform's acceleration? There. Okay, so first Will the platform accelerate? Why does it accelerate? Well, it accelerates for the same reason that the rifle recoils in the problem in one of the previous videos. Right? So if I can think of this gun before it fires any bullets, then it's a system at rest, and the total momentum of the system is 0. So as this thing fires bullets, it's going to impart momentum to the bullets leaving the end of the gun, right? If those bullets are gaining momentum to the right, well, then the rest of the assembly must gain some momentum equal in magnitude, opposite in direction to the left, right? Again, that's Newton's third law. Okay, so what is that platform's acceleration? Okay, well, I'm going to go up to our definition of momentum up here, right? dp dt is mass times acceleration. There. Okay, so what I can do is well, let's think about how to approach this, right? This is what I'm looking for, right? The acceleration of the platform. That's going to be the mass of the whole platform, right? That's the 1,000 kilograms. Right? This is the change in momentum per change in time, right? Well, how can I find these out? Well, if I look at what I'm given here, it's actually rather straightforward to figure out what's the change in momentum per bullet, right? Mass times change in speed, right? 100 gram per bullet, 500 meter per second, change in speed per bullet, right? And then it's actually rather straightforward to figure out the change in time as well, right? So if it fires 10 bullets per second, then a bullet is fired every 1/10 of a second, right? It takes 0.1 seconds to fire each bullet, right? So each bullet fired, right? Each bullet gains momentum 100 grams times 500 meters per second every 0.1 seconds, right? That's the time interval, right? So in this case, dp here is actually going to be 100 grams or 0.1 kilograms times minus 500 meter per second, right? So why minus 500 meters per second? I probably don't have to pay that much attention to the signs in this problem because it's going to be obvious from the beginning, just looking at the picture and what direction things are going to be moving. But we really do want to be strictly correct in problems like this so that we can carry that good practice over onto more complex problems, right? But if I say this direction is positive x hat, right, the bullets are gaining momentum positive x hat, this here is describing the acceleration of the platform, right? This is the mass of the platform. This is going to be the change in momentum per time of the platform. So if the bullets are gaining some momentum dp, right, the platform is gaining some momentum minus dp, right? That's where this minus sign comes from, right? Because this equation is describing the behavior of the platform. Right, so the bullets gain momentum in the positive x direction. The platform is going to gain momentum in the negative x direction, right? This has to be negative for the platform if it's positive for the bullets, right? dt 0.1 seconds there. So really, I can just solve for that acceleration in a very straightforward manner, right? Acceleration is dp 0.1 kilogram minus 500 meter per second. dt 0.1 seconds times 1 over 1,000 kilograms. There. Again, I can solve this up, right? 0.1 kilogram over 0.1 is 1, so that's minus 500 over 1,000 is minus 0.5 meters per second squared. There. Okay, so. And here's where the sign is important, right? It is important that if the bullets are fired with speed plus 500 meters per second, right, then the platform is going to accelerate in the opposite direction, right? It, of course, is not going to accelerate in the same direction as the bullets. It's going to accelerate back in this direction. Notice that this is, you look at this and you say, well, 0.5 meters per second squared, that's not that large of an acceleration, but half a meter per second squared is actually a large acceleration, right? For a platform like this, that's really just firing bullets out the other end, right? I could maybe ask slightly differently, right? What is the average force? right, that the platform feels while it's firing those bullets, and that average force turns out to be minus 500 newtons x hat, right? Well, it looks a lot bigger when you look at it like this, right? I mean, 500 newtons is a pretty large force. That would be, that's equivalent to about 100 pounds of force, right? So which is, of course, why, you get a big gun like this, and if you got, a soldier on the battlefield, that soldier is not going to be carrying that weapon around in his or her hands. Just disregarding the weight of the weapon, the fact that every time you fire it, you've got to deal with over 100 pounds of recoil force means that you're going to have to put this thing on something, right? If you're going to shoot it safely, right? And safely in this case means with control, right? Able to control it. And so this is maybe a better illustration of just how strong the recoil force than this is, right? This is after you've put it on a 1-ton platform, right? 1,000 kilograms is a metric ton, right? So that's not a light platform to put that weapon on. Okay, but I think that's a very good illustration of the utility of defining Newton's second law in terms of momentum, right? Rather just in terms of mass and acceleration, right? F is dp dt rather than just m times a. Okay, let's look at another problem here, right? And this one is going to be a little bit more complex, but a little bit more interesting as well, right? I want to look at the case of a rocket, right? So a rocket is interesting because a rocket, throughout its motion, doesn't have constant mass, right? So mass is not constant, right? And that's, of course, because of how a rocket works, right? When you set up a rocket and you fuel that rocket, most serious rockets that you're going to use to do something like launch a satellite into orbit or send someone to the moon, those rockets are 90% fuel or 95% fuel. Almost all of the mass of that rocket is in the fuel. And the way the rocket works is basically it pushes itself up by throwing fuel out the back. And of course, the only reason that you burn the fuel is in order to throw the fuel out the back as fast as possible, right? So kind of the whole point of a rocket, the rocket is really just a machine to take fuel and throw it in one direction as fast as you possibly can so that you can travel in the opposite direction as fast or as efficiently as you possibly can, right? So the mass of the rocket's not going to be constant. It's constantly getting rid of fuel, so the total mass of the rocket is going to be constantly decreasing, right? Until, of course, all the fuel is gone. So that makes these problems a little bit more interesting and a little bit more challenging. So let's define some parameters, and I'll ask to calculate a couple different things, and we'll see where we go. All right, so let's say we have rocket with some initial mass, big M naught, there, right? And let's say it ejects fuel, so it burns the fuel and ejects it at some mass rate, dm dt, right? So that's kilograms per second, right? Some rate, let's call it R naught, right? For mass burn rate, right? This is going to be in kilogram per second, there. And it does that with some exhaust speed, VE, right? So R and VE here are constants, right? And it's true that those, thinking of those as constants is a good description of how a rocket works, right? It burns fuel at some constant rate. It exhausts the fuel out the back of that rocket at some constant speed, there. Right, so exhaust speeds for a rocket are typically something like 2 or 2.5 kilometers per second, right? That not kilometers per hour, kilometers per second. It's about 2,000 meters per second. Fuel burn rates are very different for each rocket, and we can look at some samples of those in a little bit. But before we put in numbers, let's see how far we can get, right? Let's ask as maybe a first question, A, calculate A naught, right? Where A naught is the initial acceleration of the rocket. Right? So you put the thing on the launch pad, you do the countdown, 3, 2, 1, ignition, and the rocket lifts off, right? What is its acceleration when it lifts off, right? A naught, its initial acceleration. Okay, so let's go back to Newton's second law and see what we can do with this, right? dp dt is equal to m times a, there. Okay, well, right, so that's Newton's second law, right? F, m times a, I'm writing it as m times a here because I already know I want to find the acceleration, right? It's change in momentum per change in time. Okay, if I'm looking at the initial acceleration, right, I'm looking at the instant the rocket is fired, so a naught here, right? And this m is going to be the m naught, right? It's going to be this guy up here, right? M naught times a naught, then. Right, where that mass, I don't need to worry about the variable mass here because I'm looking at just the instant when it's fired. I'm not looking at a time interval, right? Right when it gets launched. Then, okay, so let's write this. M naught a naught is dp dt. That's d m v dt. There. Okay. So what's the change in momentum of the rocket then? Okay, so here's where the idea of conservation of momentum and impulse comes in, right? So the change in momentum of the rocket is going to be same in magnitude to the change in momentum of the fuel, right? Just in the opposite direction, right? That's Newton's third law coming into play here, right? So what's the change in momentum of the fuel, right? Well, that's the change in mass of the fuel times the speed of the fuel over change in time, right? Okay, so the mass of the fuel is not going to be constant, right? The mass of the fuel is going to be variable. That's going to be changing all the time, but the speed of the fuel is going to be constant, right? I know I've got exhaust speed VE. That'll be constant. That can come out of the differential, right? VE dm dt there. Right, and I know dm dt, right? I don't know what dm is, and I don't really know what dt is, but I know that rate, dm dt, is some constant rate r naught, right? That's the fuel burn rate, right? Naught a naught is VE times r naught, right? And I can solve this for the initial acceleration. VE times r naught over m naught, right? Right, it's the initial acceleration of that rocket, right? Depends on the exhaust speed, the fuel burn rate, and the initial mass of the rocket. And so you can kind of see a little bit about how a rocket actually works here, right? Generally speaking, right? Especially if you don't have a person in that rocket, right? If you're launching, some satellites, just by itself, or some inanimate payload into space, right? You really want to try to maximize this A naught. You want to get that as large as possible. In order to do that, right, you can do kind of two things, right? You can increase exhaust speed VE, you can increase the fuel burn rate R naught, right? So really what a rocket engine is kind of designed to do is to burn fuel as fast as possible and shoot it out of the back of the rocket as fast as possible, right? Initial mass m naught a lot of the time is somewhat out of your control, right? I mean, you have a certain payload. The payload has a certain mass. The fuel has a certain mass, right? So that is kind of set. Although, as much as possible, you want to decrease this also. Okay, so let's kind of take a couple numbers from a pretty well-known rocket, right? I'm going to use the Saturn V rocket as an example here, right? And the Saturn V is the rocket that took all of the Apollo missions to the moon, right? So Apollos 11 through 17, right, went to the moon on Saturn V, right, and then the previous Apollo missions, went up into space as tests on a Saturn V, or sometimes on a previous rocket, right? But we're taking the Saturn V, right, the rocket that actually sent the Apollo missions to the moon, right? Right, so let's take a couple parameters of that rocket, right? That has an exhaust velocity of about 2550 meters per second. It has a fuel burn rate of about 2200 kilograms per second there. And yes, that's kilograms per second, right, of fuel burn, right? You think about that, that's just kind of an amazing number, right? You're burning 2 tons of fuel every second out the back of that rocket, right? It's just kind of an amazing thing that a machine can be designed and built that will actually burn fuel that fast and not explode while doing it. In fact, there's kind of a joke amongst rocketeers that a rocket is really, when it comes down to it, a rocket is just a barely contained explosion, right? And this is kind of why, right? You're burning this much fuel per second. It really is just a barely contained explosion. And the launch mass of the Saturn V was about 480,000 kilograms. Then, yes, you can calculate the initial acceleration, right? That's actually not that hard, right? A naught, VE, 2550 meters per second times 2200 kilograms per second over 480,000 kilograms. And that comes out to be about 11 and change meter per second squared. There. Okay, so that's actually a pretty good acceleration. It's a little bit more than g. Notice though that when you launch the rocket, it's not actually going to accelerate upwards at 11 meters per second squared. It's actually going to accelerate upwards at something like 1 or 2 meters per second squared, because g is about 10 meter per second squared, right? So the actual acceleration of the rocket will be the acceleration provided by the engines minus g, right? Gives you an A, and kind of a net acceleration of about 1 meter per second squared, then. Which does not look like that much. In fact, really isn't that much. If you look at a video of a Saturn V launch, what you'll see is that after the rocket has ignited and it's lifting off from the launch pad, it looks like it's really moving quite slow, right? And it actually is, right? The initial acceleration of the rocket is quite small, and it does take a while to get up to speed. The whole point of the rocket is that it sustains this acceleration over a very long period of time, right? So, well, if you sustain 1 meter per second over 60 seconds, right, you're up to 60 meters per second, still accelerating at 1 meter per second squared. Now, 60 meters per second still isn't all that fast, but what you need to remember about the rocket is that this and this are constants, right? These don't change through the rocket flight, right? The exhaust velocity is always 2550 meters per second, and the burn rate is always the same. It's always burning fuel at a rate of 2200 kilograms per second, but this is decreasing at a rate of 2200 kilograms per second, right? So as this number gets smaller, this gets smaller, and the acceleration is constantly getting larger, right? So it starts off with 1 meter per second squared, right? But as the fuel burns, the mass of the rocket decreases, and this starts going up, right? Half the fuel, after half the fuel is gone, right? Now this is not 11 meters per second, it's 22 meters per second, minus g is 12 meters per second squared. Not 1 meter per second squared up, and now now you're at more than g going straight up, right? Or maybe not quite straight up, right? The rocket usually turns into a tangential orbit rather than a radial straight out as it gets up in altitude. You can see this as well in a lot of the launch videos, but what you'll see is you'll keep burning this fuel, and this acceleration will keep going up, right? If 90% of the rocket is fuel, then by the time you're all the way down to the last bit of fuel or near the last bit of fuel, your acceleration is something like 90 meters per second squared, right? It's 9 Gs or something like that, right? It's some very, very large acceleration. dangerously large for humans, right? It's possible to actually injure someone in a rocket if you make this acceleration too large, right? So that actually does need to be managed as well, because as the mass decreases, right, this will just keep growing, right? And there's really no way to stop it without just shutting off the rocket engines. Okay, let's do a part B to that, right? And this is going to be a little bit different, right? So same situation, same rocket, and what I want to do is calculate V final, right? How fast that rocket is moving after, let's say, burning fuel all the way down to some final mass, M final, right? So the rocket has some kind of fuel in it, right? It has kind of a starting mass of m naught, right? Minus mf, right? That's, mass of fuel in the rocket, right? So that's fully loaded weight on the launch pad. Final mass, right? That's the mass after it's burned all its fuel, right? The difference is, of course, the mass of the fuel in the rocket. After it's burned all that fuel, how fast is it going? Okay, so that's the question I want to ask now. Okay, let's set up with Newton's second law again. M times A is minus V naught dm dt there. Okay, so y minus v naught dm dt, right? Well, because this is, for the rocket, right? For the fuel, right? M times A is V, not V naught, VE, right? Exhaust fuel, VE, dm dt there. Okay, so for the same reason as in problem 1, right, the machine gun problem, right, I've got this VE, that's the exhaust velocity of the fuel. If I'm describing the behavior of the fuel, I've got mass times acceleration is VE dm dt. If I'm describing the behavior of the rocket, right, the rocket has a change in momentum opposite the direction of change in momentum of the fuel. I need minus VE dm dt here. And okay, so let's see where we go from here. Now, of course, what makes part B more challenging than part A is that the mass here is not constant. That's not just m naught or m initial anymore, right? That's now I'm looking at what happens to the rocket from in the time interval, right? The time interval between launch and burning out all of its fuel, and m changes there. Okay, so that's going to be a variable. That's a function of time. That's m of t. Then. Okay, well, I've got m of t here, and I've got dt down here. I'm going to see what we can do if I try to get some of these together, right? Let's get the dt on this side of the equation there. So I have a dt, and I'm going to bring the m over here, minus v e 1 over m dm there. Okay, that's this. So 1 over mdm is something I like, right? I like to see this because I can integrate this, right? Integral 1 over mdm, right? It's actually not a very hard thing to integrate, but I'm not sure what I'm going to do with this side over here. What I think we'll try to do is define A as dv dt, all right? That'll give me the v that I need as well, all right? So if I define A in terms of velocity, right, that'll give me what I'm looking for up here. dt is minus ve 1 over m dm, and those will cancel out, leaving me with dv is minus ve 1 over m dm, and that's something that I can do some calculus with, right? So let's go ahead and do that. Let's integrate this from some v naught to v final dv, and this is a constant, minus ve. And let's integrate this from m initial to m final, 1 over m dm. Okay, so from initial mass to final mass, the rocket will increase in velocity from some initial velocity, which we'll just call 0, to some final velocity. Okay, so this is easy, VF minus V naught. Okay, what about this then? Minus VE. Integral of 1 over m is natural log of F minus natural log of m naught there. Okay, I'm going to, V naught here is 0. The rocket starts at rest. VF is, I'm just going to take this negative sign and distribute it here so that this is ln m naught minus ln mf there. Okay, and if you remember your natural log arithmetic, this just becomes ln m naught over mf, right? That's how logarithms work. It's kind of a logarithmic identity, right? ln a minus ln b is ln a over b. There. Same with, you know, any base log. Log a minus log b is log a over b. There. Okay, that's what we're looking for, right? That's final velocity after burning fuel from initial mass m naught to final mass mf. I got exhaust velocity right here as a constant. So if we go back to the Saturn V again, right, I'm going to write down the Saturn V specifications up here. The exhaust velocity was 2550 meters per second. The initial mass was 480,000 kilograms, right? If you can look up what the empty mass of the Saturn V is, the empty mass is about 36,000 kilograms, right? So look, I mean, huge difference between fueled mass and empty mass, right? The vast majority of this thing, 96% of this thing is just fuel. Okay, so let's plug those in, right, and find VF, right? If I do that, and if I plug in 2550 meters per second, natural log of 480,000 over 36,000, I get 6605 meters per second, right? So that's about 6.5 kilometers per second, right? That's very, very fast. Okay, but notice that that's not really fast enough, right, to match Earth escape velocity, which is about 11,000 meters per second, right? You know, it's just a little bit more than half that. But the Saturn V obviously did, break the pull of Earth's gravity, right? You know, certainly enough to get out to the moon, which is quite far. In fact, the actual velocity of the Saturn V, right, the maximum velocity of this thing was about 10,200 meters per second or so, man. Okay, so there's a couple of questions that we have to ask here, right? Why is there such a big difference between what we calculated here and what the actual launch velocity was here? The real answer to that question is that the Saturn V the Saturn V wasn't just one big tube that burned all that fuel all in one go, right? So check out a video of a Saturn V launch sometime. And what you'll see is that as the rocket rises into the air, sections of it drop off, right? That rocket fires in stages. So what it does is it burns a whole lot of fuel, but not all of its fuel, maybe something like half of its fuel or 60% of its fuel, and then it drops all. You can see. One huge section of the rocket, which is now empty, drops away, right? And that actually greatly decreases the remaining mass of the rocket, right? And it means that whatever fuel remains needs to accelerate a smaller mass so it can accelerate it with a larger acceleration and more efficiently, right? This VF goes way up, right? If you drop away stages of that rocket, right? And this, of course, that's the whole reason why large rockets like that are launched with booster rockets, like the Space Shuttle had booster rockets, or in stages, like the Saturn V had stages, so that empty parts of that rocket can fall away and you require much less fuel. Or you can get a much larger velocity up to this with the same amount of fuel, right? A single stage rocket could, the size of the Saturn V in a single stage would reach a velocity something like that, right? Multiple stage rocket, increases that by about 50%. You get a huge gain in final velocity after that. Now, the reason why that wasn't quite up to Earth escape velocity is because, well, actually kind of for two reasons. One, because you actually don't need to fully escape the pull of Earth's gravity to go to the moon. You can still feel the force, gravitational force of Earth when you go to the moon. It's not zero. Clearly, it's not zero because it's strong enough to keep the moon in orbit around the Earth. So you're not actually escaping Earth's gravity. You're just getting very close. Right? The other reason is, of course, as you're traveling to the moon, you can use the pull of the moon's gravity to kind of help you out. So you also don't, those two factors mean you don't need to get quite up that high. Right? Okay, that's a really good problem. I think a rocket like this really illustrates just how powerful defining Newton's second law, right? Ma is dp dt. Right, just how useful something like that is, right? That's where we started like this, right? There's really, no other really good way in order to do this. Just F equals ma won't really do it, right? You really have a hard time doing that if the mass is not constant, right? But you can do it with this, right? Which is very handy. Okay, I think that's where we will end the video for today. Look out for in-class exercises with problems like this, and I will see you next time.